My heritage is Italian, and I can't really sit still ever. So I like to wander. So I find this a little bit, confining. So I'm going to stand here. And as Cynthia mentioned, I've been doing Arctic research, which is my main area, since I started my master's here in 1994. I look pretty good for my age, I think, maybe? No? And back then, I used a lot of remote sensing and GIS, so I've seen the evolution of GIS as it's progressed from almost command line to now a lot of user interface and a lot of extensions that are available to everybody. So I'm going to focus on changes in the marine cryosphere that I've studied, and put a little bit of focus on, at the end I'll emphasize why it's important to study this, and focus mainly on Arctic marine mammals, which is my area of interest. I'm also part of the Arctic Science Partnership, which is I guess a consortium of the University of Manitoba, Aarhus University in Denmark, and the Greenland Institute for Natural Resources in Nuuk, Greenland. And we're working together to kind of break down some of the barriers in terms of research, teaching, and outreach, so we could work together as a unified thing to study the Arctic. And I'm also a member of the Center for Earth Observation Science here at the University of Manitoba, where one of our main focuses was use of remote sensing and GIS. So as a presentation outline, I'm going to focus a little bit on why it's important to study the Arctic cryosphere, focusing primarily on sea ice and snow, being the two main components that we focus on and that I focus on. I tell everybody that snow is the most important part of the marine cryosphere. It's also the most important part of any system. That might be a little biased, but I believe it wholeheartedly. And then I'm going to talk a little bit about the use of geomatics for cryospheric research, why it's a useful and I would say an imperative tool for us to use. And that includes both remote sensing and GIS. I consider them going hand in hand. One's a product, one's a program that is used to analyze that product. And then I'll talk about the changes in sea ice and snow cover that I've studied and looked at, why it's important. And I always have to show obligatory photo of a polar bear. This was one we've taken when I was flying in the Arctic. There's a mother and a cub. At the time, we were doing something we weren't supposed to do. We were chasing it. The pilot wanted to see a polar bear, so he got his wish, and we kind of chased it a little bit around, and then we stopped. We didn't want to stress it too much. But there's no evidence that we chased it, and I will deny it to anybody, any agency out there. So why is it important? Why is the cryosphere important? Why is snow and sea ice important? Why do we study it? Well, first of all, it affects the physical system, including the climate, the energy budget. You can see, oops, whoa, that wasn't good. You can see here that there's a nice, smooth surface, snow-covered sea ice here. You see the sun shining, and you see the reflectivity of the surface, called the albedo of the surface. Snow, freshly fallen snow, has one of the highest albedos at 90%, meaning that it reflects 90% of the incoming solar radiation. So very little makes it into the system. Most of it is reflected away. Sea ice has a slightly lower amount of albedo, so it really controls the environment, and that will control the fresh water, or the hydrosphere. It controls the other physical components of the system. It also affects the biology. Sea ice isn't a dead environment. You have things living on top of it, like the polar bear, that utilize the sea ice for all parts of life. They hunt on it, they mate, they do everything. When they go on shore, they typically don't do anything. So sea ice and snow-covered sea ice is critical to them. It also affects large mammals in the water, like seals and whales. It'll affect fish. There's things living in the sea ice itself. There's bacteria, there's viruses, there's algae that are growing on it and within it. So it's not a completely dead environment. There's a lot of biological activity in it. So it's important from the biological perspective as well as the physical. And then the last component is the social component. Sea ice and snow-covered sea ice is important for Arctic communities. It could be used as a traffic corridor once the islands in the Arctic are frozen over, or the area between the Arctic are frozen over. Inuit can use it to go from one location to the other, using dog sleds, snowmobiles, things like that. It's a hunting ground for humans as well as whales or bears. So it's important in all components of the system. So how does geomatics used for our research? Why is it important to utilize geomatics? Well, the first one is, if we talk about the advantages, is the ability to monitor the environment year-round. The Arctic is really accessible only for a maximum of about half the year, and if you think about getting there, it's a vast system, it's a vast area, and half the time it's cloudy, half the time it's dark. So it can really impede a lot of what we could do and some of the research that we study in the with regards to Arctic processes and cryospheric processes. So the use of remote sensing in GIS gives us a way to analyze it without necessarily having to be there and having to deal with the logistics of getting there. It's very expensive. You set up a field camp, which could add time and money to projects, things like that. Day and night ability, again, you don't want to go to the Arctic when it's dark. It really limits your ability to do research. The use of remote sensing and GIS allows you to investigate processes like the cryosphere, which is mostly a nighttime process. If you think about day and night in the Arctic, it's going to fall, snow falls and ice forms in the autumn, melts in the spring. So it's really this dark period process. From a GIS perspective, we have a lot of data on GIS or on the Arctic that comes from remote sensing and other avenues like the Canadian Ice Service with their ice charts here. The volume of data is a lot, and if I had to go through each one of these ice charts manually to analyze it, these are produced every week in the Arctic for 52 weeks, so you have every year 52 different images. And I'll show you some of my research, which goes back to 1980 to see spatial patterns and temporal patterns. It would be an onerous amount of work to do. It would almost be impossible to do it without the use of technology. So it becomes a key component to any analysis we do. And also it allows us to objectively analyze data without having to go through these visually and look at how different sea ice types, that's the different coloration in these images, different sea ice types and concentration, without having to do this individually and in a very subjective way, looking and seeing how things change based on just visual clues. I can throw them into a GIS, analyze them. I can leave for lunch, come back, and everything's analyzed and I have a nice chart, and it's great for research. When I started in 1994, it was almost impossible to do that. It would take days to hopefully get the program to work, leave it running overnight, coming back to the lab, noticing that somebody turned the computer off. It happened to me many a times, and then having to restart the whole system again. And of course, like a good student, I didn't write anything down, so I'd have to figure it out what I wrote and how I did it. It happened more than once. Maybe that was my bad. But the last component I just want to talk about is the emphasis on the spatial component. As a geographer and as somebody that studies movement or habitat of Arctic marine mammals, why they go where they go and what controls where they go, space is an important component of that analysis. And that's really I'm only able to do that in a very objective and effective way using a GIS. Bringing all that data in, that vector data with the raster data of satellite imagery. This is the vector data. I have movements of bears, another vector layer on top of that, and I could really look at those different data types in a very effective way, an efficient way. So now, having said that, what have I found? So I'm going to talk about changes to snow and sea ice. I'll talk about sea ice first. We hear a lot about changes to sea ice in the news, especially in the Arctic. And what I've done is a study that looked at temporal and spatial changes of sea ice type in the Canadian Arctic. So, and I used Canadian Ice Service ice charts that are available online. You can go download them. They're easily imported into a GIS. And I used from 1980 to 2012. They have ice charts available before 1980, but the way they use an egg code, and they changed the egg code between 79 and 80. So I only went back to 1980 just to make it simple. And then what I did was I took the ice charts, and one of the ability of GIS was I wanted to look at part of my project was to look at how those changes, how sea ice had changed, but more importantly, how it changed for different polar bear populations. So on this map, these areas that are bounded by the solid lines here are different polar bear populations in the Canadian Arctic. You hear a lot about what's going to happen to polar bears. They're going to die out because there's less sea ice. That's a very general statement, and it's very specific to certain parts of the Arctic. In other parts, polar bears in the short term will do very well because of sea ice changes. So what I wanted to do is look at how sea ice changed within this entire area, but dividing it into these different subgroups or these different polar bear population zones, management zones. So what I found, and I'm going to show you a lot of these graphs, and I apologize, these are a little small, but so I looked at a number of different parameters. So I could, because these ice charts are very informative, they're easy to access, and I can bring them into a GIS rather quickly. They hold a wealth of knowledge, of information in them. One of them is whether ice is there or not, the very simple parameter. So I looked at open water, and all of these squiggly lines are for the different areas. So these are the areas around Hudson Bay. These are the ones in the Canadian Arctic, and these bottom ones are the ones in the Beaufort Sea, so around here. And what I found for open water, this is for summer. I did the same thing for the autumn period. And what you see is that over time, as we get closer to the 2000s, you're getting more and more open water, which kind of doesn't surprise a lot of people, didn't surprise me. So there was this trend in open water. It wasn't as evident in the Beaufort Sea, and there's reasons for that. Beaufort Sea, you have a gyre that forms in terms of transport of sea ice. So sea ice might not form there, but it's transported in because of the movement of the gyre. So a lot of this has to do with the fact of how strong the gyre was and how much ice was formed in other areas. But for instance, in Hudson Bay, you see this nice upward trend, again indicating less and less sea ice or more and more open water as the years progressed in these three management zones here. And what I was able to do in a GIS was I found these trends, but I wanted to look at what was creating them, whether it was pressure or whether it was temperature, those being the two primary ones that I had data available for. Precipitation, you don't have a lot of information for precipitation in the Arctic. There's only a few stations, and what I found in other research was that a station on land and what was happening on the sea ice were completely different. So it's hard to use a Churchill weather station to look at what's happening on the eastern side or in Fox Basin up here. So I didn't use precipitation. So what I found was that temperature obviously was a good correlator for this change. There was a positive correlation for most of the areas that I was studying in the summer and in the autumn. I did the same analysis for the fall. So you see that most of it, especially around in Hudson Bay, there was a positive correlation, and it was typically a lag of one season, meaning that in the summer, it was really the spring temperatures that were affecting the summer sea ice concentration, which made sense. For open water, atmospheric pressure indicated by the Arctic Oscillation, a large-scale estimation of pressure in the Arctic, it wasn't as correlated. You didn't see a lot of correlation in most of the statistically significant correlations in most of the management zones, a few in the high Arctic, but these might be, I'm hesitant to say that these are highly significant. I think it was due to another factor in terms of open water. Did the same thing for different types of ice, because again, there's more information than just whether ice is there or not. So I used it to look at first year, and I also looked at it to use this method to look at multi-year sea ice. First year sea ice being the primary polar bear habitat in the Arctic. They love first year sea ice and especially rough ice. Multi-year ice they stay away from. It's not a good seal habitat. So again, you see a lot of lines. This one didn't come out very well, but you see that, and I'll just focus on Hudson Bay being these ones up here. You see that first year ice concentration has declined. Well, if you get more open water, there has to be less sea ice, so it was kind of intuitive. And there's no real multi-year or old ice in this region here. So you see this nice decline happen in those regions. There's some interannual variability, but you see, especially in Hudson Bay, this nice decline. And when you correlate it with, so down here with temperature, what you see is that again, in Hudson Bay, it's correlated again, so there was a positive correlation for summer and as well as the autumn in Hudson Bay, as well as other regions in the Canadian Arctic. You don't see a significant correlation in the center, in the archipelago, because of you have significant topographic factors. You have pressure is going to be of influence, winds, things like that, are also going to affect ice concentration, especially first year ice. Once it starts to get mobile, it gets stuck often in that area. And the third parameter I could look at, and I did look at, was different, not different types of ice in terms of age, but different types of ice in terms of where it's located. So one of those is fast ice. This is ice that is connected to the land. It doesn't move once it's formed. It's fast. It's faceted to the land. And then there's mobile ice. And again, Hudson Bay, very little change. There's very little anomalies here annually. The Canadian archipelago, there's a lot more anomaly. It's moving a lot more. There's less one year, a lot more another year. And then again, correlated pretty well with summer temperatures. You see this negative correlation. So as you're getting higher temperatures, you're getting less fast ice, and not so much correlated with pressure, as indicated down here. Pressure wasn't a good indication of, or the Arctic oscillation wasn't a good indication of what was happening with ice. Again, this is something I couldn't have done without GIS, without the use of the ice chart. So it really helps to analyze this on this spatial component as opposed to just looking at broad scale, and especially with polar bears, painting their habitat change with a broad brush, because it's very unique to different management zones. Another one is what we define as breakup, or ice absence states. Breakup I defined as the date at which ice concentration falls below 5/10. So when there's less than 50% ice cover. And for this study, we were studying the area close to between Churchill and James Bay, and just the area close to land, offshore of land, and we divided it into these 5 different areas. That's what you're seeing with all these different lines here. The first 3 we characterized as all one group because of its. These are bears that come from James Bay and stay around those areas. Bears have a high fidelity to specific areas. And then we have the Churchill population, subpopulation, and then we have the one in between. So what we saw is, again, we could do this nice analysis, and this I'm constantly updating every year. It takes me 20 minutes in my office once the time comes, where I can estimate what the breakup date is for these 5 different areas, or for the Western Hudson Bay subpopulation, as well as indicated by this line here. This is the Churchill polar bears. And what we've noticed is that there's this overall this temporal decline, but a lot of that interannual variability. And we use that to look at, in this study, what the population of the polar bears were doing. What condition were they in? We had a lot of information on how many cubs they were born, how many survived, the fat we found on the bears when we sampled them, things like that. So we could estimate it based on that nice fine temporal resolution, and we saw that there was a nice correlation between the breakup and absence states and the condition of polar bears within these 5 different regions. If we talk about snow cover changes now, I did a study recently looking at ring seals and snow cover. Ring seals, in order for them to have favorable habitat, they need a certain ice roughness, which will catch a certain amount of snow. So you need nice snow depth on it, deep snow that they could build their layers to give birth in. So what I used was remote sensing data, AMSR-E, which has now been is non-functioning well before it was supposed to. So I only had a few years of that. Maybe it was, I believe, 8 years of data from AMSR-E, which is a satellite. And then I also used a regional climate model to project out in the future. And I put all this data into the GIS. I ran it, went for coffee, came back, and had nice graphs produced that, and all it needed to do was write the paper for me, and I would have been happy, but it didn't. So I used this study area. We were looking at, again, the Western Hudson Bay area. That's one of the most researched areas in terms of polar bears and ring seals, so we have a nice biological data set. And I did this study with Steve Ferguson at the Department of Fisheries and Oceans here on campus. And this plot here, it's not turning out well here. Didn't turn out well in the paper either. But what it was trying to show was the trends, the spatial trends in the snow depth based on the satellite imagery that we had. So instead of taking it and again painting it on a broad brush for even that area, Western Hudson Bay, what I wanted to do was look at how the snow was changing temporally, but on a very fine scale. So I could identify areas of hotspot for ring seals, areas where they were declining from 2003 to 2010, the satellite period that I had. And what you see is a lot of interannual variability. There are areas in the northern part of the section that had significant increases in snow depth for some years, areas that were closer to the mainland, which had significant decreases in snow depth, probably attributed to blowing snow. So again, showing that fine spatial resolution that I could only get with the GIS and the remote sensing product I used. And then I modeled it. This was data available through the Canadian Center, the Climate Center in Victoria. They produce a model. They run one of the Canadian global circulation models, and I used their output for Hudson Bay to look at the temporal trends. So this went out to 2010. Try to think about what may potentially happen in terms of seal densities and therefore related to polar bear habitat well beyond our instrumental record into the future. And what I noticed putting it into a GIS, running it, was that, and it gave me these nice graphs where you could see the significant decreases in snow depth, especially in the winter. In Hudson Bay and in the Arctic in general, you get a lot of snow in the shoulder seasons. You get a lot of snowfall occurring in the summer or in the spring, and then a lot in the fall, very little in the winter. So most of the change that I saw was happening in the winter season in terms of the snow depth and also the snow cover duration. So the period from when you started to get snow and when there was something to catch the snow in terms of ice to when the ice was off and there would be nothing to catch the snow. And again, we see this nice significant decline in snow cover, in snow throughout that period for the same area, suggesting less and less snow, and the period that it's going to be there is going to get shorter and shorter. So from a ring seal and a polar bear habitat perspective, this is the problem, is more the duration rather than the depth. So the implications for these changes, well, one of them is a physical, and I'm just going to highlight three. If you have a white surface that's snow covered, snow and ice covered, you're going to get a high reflectivity, as I mentioned. About 90% of the energy coming in is going to be reflected away. You remove that, and now 90% is going to be absorbed by the oceans. So you're going to get a lot more absorption. The system is going to get warmer, and it's known as the Arctic amplification of climate change, or global warming. When you remove the white lid off the planet, you're going to create a different system, which is going to behave differently. It's also going to have biological impacts. So as I mentioned, one of the things I'm doing, and I still do to this day, is I analyze the breakup date using a GIS for Western Hudson Bay. And this was a study I did I published in 1999, so it's 16 years old now. It still gets cited even to this day. And what I did was I calculated the mean date of breakup in terms of how it's changing. And you can see even in this short time, the 7 or 8 year cycle period, you see the significant decline in breakup is occurring earlier in terms of the Western Hudson Bay. And this is the date that the bears were coming ashore. So this is the onshore dates for polar bears that we had collared. And the numbers here just indicate the number of bears. So I just want to highlight that there are not a lot of bears that we collared that came ashore. But you see this nice trend. They're very similar to one another. And when I plotted this, I worked with Ian Sterling, one of the Canada's preeminent polar bear biologists. I was working with him at the time, on this study. When I showed him this graph, he almost fell off his chair. He couldn't believe it was so nicely in sync. I think one of the first questions he asked me was, what did I do to the data? How did I fix this? I didn't fix it. I didn't manipulate it at all. But you see this nice trend, and I think it was at a 90% level of significant or of association between the two lines. Again, indicating that there's this nice association between breakup date and when the bears were coming ashore, and it was about a 2-week period between them. So if we can capture the date that the sea ice is breaking up, we can estimate when the bears are coming ashore. And as you can imagine, they're coming ashore, as probably you know, they're coming ashore earlier and earlier every year. And when they come ashore, they're not doing much of anything. They're playing a little bit. The females are having their cubs, and then the males are really waiting for the ice to come back. So they're not feeding. So that's it. That's all I wanted to talk about. So if you have any questions, I'm more than happy to answer them.